Now you'll recall at the end of our previous lecture, we had just balanced the pressure inside the shell times the surface area of that against the rate of change of momentum of the shell as it expands. Now, that gave us an equation that looked like this, which was epsilon u naught squared rs squared is equal to 1/3 times the time derivative of rs cubed over u, or times u naught, bracket there. And remember, epsilon is a scaling term which relates the pressure just inside the shell, so just as it hit contacts to the outer part of the interstellar unshocked gas, to the average pressure across the shell itself. And it's some factor which is less than 1 that will work out as we move along. So note we have 1/3 times the time derivative in the end of the previous lecture. I may have had an extra 1/3, which was incorrect. Okay, so now what is d dt? Well, d dt can be rewritten in a number of different ways, and we're going to rewrite it in a way which allows us to take the derivative a bit more straightforwardly for the type of data that we're working with. So you could write it as r dot times d dr. That would be one way to do it. Or it could be written as the partial derivative with respect to time plus u partial derivative with respect to radius. And that should look to you like a difference between an Eulerian and a Lagrangian. And in our case, we can let this partial derivative will be 0. And so we can rewrite our d dt as a u delta r. So where do we go from that? Well, we take the derivative, the time derivative of the equation up here that we have our d dt, and we'll just swap these two sides. So we write down that, let's write down one more thing. Let's also recall that the speed u naught can also be described as rs dot. So it's the time derivative of this shell. And that's an important relationship that we'll work through. So we can rewrite our equation above in white as 1/3 times 3 rs squared, rs dot squared, plus rs dot rs cubed, partial derivative of rs dot with respect to r is equal to epsilon rs dot squared rs squared. Okay, let's see if we can cancel some things out. So what can we cancel out? Well, we can cancel out the squared here. We can say this one cancels. We can say that this one cancels. That cancels there. All with the bits over on the other side over here. So we move on to determine that rs dot plus 1/3 rs partial derivative of the derivative of the radius, so that would be the second derivative, delta rs is equal to epsilon rs dot. And this equation can be solved with a relatively simple function. So we can solve the partial differential equation, and we solve this with the equation rs dot is equal to a, which is some constant, times rs, 3, times epsilon minus 1. Okay, So that's a pretty big result. So where can we go from there? We can take this, we can go back to our energy equation, which we originally said related the kinetic energy of the shell plus the thermal energy of the shell to give us RS for fixed energy. And that's what we're going to do in the next lecture, which we'll pick up on in just a few minutes.